Okay, next part. It says describe. So we're on the radioactivity bit, and I think you'll do really well on this. So it says describe the structure and properties of alpha, explain why it has the highest ionization levels, and why is it a risk as a contaminant. All right. So it's made of 2 protons and 2 neutrons. Mark. It's a fast, large, positive particle with lots of momentum. They're hard to stop. So they're brilliant at knocking out electrons from atoms and forming positive ions. All right, so that's why they're good at ionizing. So you can imagine if we've got a small, tiny particle, its chance of hitting something is low. If I've got if I want to hit that X there, this has got to be perfectly lined up. Well, this thing's got loads of chances because it's big. Alpha particles are big positive particles with lots of momentum. And then the next part is, well, why? Well, alpha has got a really short range. So its risk as a contamination is, well, contamination means it is in you or on you. And therefore, you haven't got a short range. It's very, 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 very close. It's going to cause damage. Okay, what is background radiation? How can it be calculated? So it's radioactivity in the environment from rocks and air. Next part. I need to calculate it. Well, I need some way of measuring it. Get a Geiger counter. Okay, next part. Make sure there's no other radioactive sources near. All right, because I want to measure the background. Next part. Measure how many counts over 1 minute. And then we're going to repeat that 3 times to work out a mean. All right. So to do it as a picture, before I put these, we're just going to get a Geiger counter, plug it in, have a stop clock, and we're going to make sure there's nothing around, completely empty space so that it's not being contaminated. And then our Geiger counter, we're then just going to time for 1 minute, and let's say it's 452, that's background, and obviously that'll be pretty tragic as a background. So to go over that again, get a Geiger counter, make sure no radioactive sources are near, do the counts over a minute, and repeat it a few times to get a mean. Okay, describe the radioactivity penetration test for alpha, beta, and gamma. First part, I need a source of radioactivity. That's there. Next thing, I'm going to get a Geiger counter. That's a mark. Okay, now this gap needs to be small because we know alpha can't go very far, so we've got a small gap. Okay, now we just go through. First thing in, paper. If it gets stopped, it is alpha. All right, so if you get stopped, it's alpha. Next thing, and I'm going to put my alpha there. Well, after I've put paper in the way, and if it stops it, next thing I'm going to go with thin metal. If that stops it, it's beta. Next part, thick lead. If that stops it, it's gamma. All right, but the crucial part is I get a source, I get a Geiger counter, and I have a small gap, and then I put them in order. Paper, thin metal, thick lead. And if you want to go 2 millimeters, 2 plus centimeters. All right. Okay, next one you should be really good at. What is the time required for a source with a half-life of 2.5 days to go from 400 to 50? So I've taught you 400 and put a start underneath. Half it, half it, half it until you get to what you need, 50. We can see that that's 3 half-lives. Well, then I go 3 lots of the half-life. So 3 times 2.5 equals 7.5 days. Next one, use the graph to calculate the half-life. So we're going to circle 140, half it to 70, go across, read it down, and you can see we've got, I'm going to read it like that, my graph works rubbish, 1.5 minutes. Gives you a tolerance either way. And then the last part is, radioisotopes for medical tracers are made in the hospital right before use. Why are they not stored? So they have short half-lives, a mark. So they need to be used quickly so there is enough radioactivity to detect. All right. If I store it for ages, by the time I open the bottle, there's no radioactivity left. So it's this idea, got to use it quickly so I can detect something when I put it in the body. And that, I believe, is it.